All right. Okay, so this looks like a complicated formula, right? A equals A sub 0 e to the kt. So it says in our last adventure, a little while ago, we looked at compound interest formulas, and A equals PE to the RT was used. That's all this formula is. A is the amount in the account or the population or the amount that you end with. P we call principal when you're investing, but A sub 0 just means your initial amount. So the initial population, the initial amount of carbon that's present if you're radioactive carbon dating, the amount of radioactive material that you start with, that's your initial amount. So A sub 0 in principal. E is our constant for continuous interest, or for bacteria growth, it's like this continuous growth. K is a constant. So interest rate was our constant for compound interest, but K is just a constant. So if you're decaying at a certain rate, if your population is growing at a certain rate, we have to find out what K is. And T is still our amount of time, so days, months, years, whatever it is. So it can be used for all exponential functions. And then, so I just explained this. Oh, if K is positive, then our function is increasing, like positive interest rate or population growth. But if K is negative, then the exponential function is decreasing. So if it's radioactive decay or the cooling temperature of coffee or tea or pizza, K is going to be negative because the temperature is going down over time. So we're going to become kind of fluent with these few terms and constants. Classic examples of increasing, compound interest, I already said, population growth. Classic examples of decreasing, radioactive decay, or car depreciation, right? Your car goes down a certain percentage each year in its value in the Kelley Blue Book or list price or whatever. All right, so the simplest applications are when you already know your starting amount, your K value, and the amount of time, just like we did with interest. So example one is just, we've got the size of a certain insect population in days, can be modeled by this equation. Population equals 500 is the starting number of insects, E, so that's representing our continuous growth or decay. To the 0.02 is my K value, and T. I'm going to plug in how many days, and it'll tell me the population. So what's the population after 1 week? I'm going to plug in 7, right? 500 E to the 0.02 times 7, and it's just going to spit out the answer for me. Not a complicated process at first. So 500 E to the 0.02 times 7. So if I round to the nearest insect, it would be what, 575 insects? So that's great. Once you have a function, now you can just plug in your time. Same thing like COVID-19 at the beginning. It was an increase in number of cases. They could plug in how many days and figure out how many cases there should be. Then we started flattening the curve, so they changed which function was modeling the curve. But sometimes we know the values of how much is currently existing. We know the constant in T, and we want to solve for the initial amount. In these cases, remember that although it may look intimidating, the expression e to the kt is just a number, because e is a number that you know, k is a number that you know, and t is a number that you know. So basically, e to the kt is a number. So the size of an insect population has reached 10,000 organisms. A researcher determined the value of k is 0.05. What was the initial population 3 days ago? So the way I would set this up, my current population is 10,000. I want to find A sub 0, the initial population, and that's times E to the 0.05 times 3. So I'm plugging in K and I'm plugging in T. This is just a number on my calculator. So I can just take that number and divide it to the other side. So first you want to find e to the kt. So here's e to the 0.05 times 3. So I could evaluate that first if I wanted to, 1.16. But you want to use that whole decimal. You don't want to just use 1.16. So I take 10,000 divided by second answer, or you could highlight that number, but you want the whole decimal. 8607. I just want to show you how far off you're going to be. 10,000 divided by 1.16. So if I just round it to 1.16, see how I'm off by 13? So you want to use the whole decimal when you can. So 8607 was the population 3 days ago. Does anyone need help typing it into their calculator? Are you trying it at least? You're going to have to do applications on your own eventually. So this one, we started with everything was known. This one, we started with everything was known, but we had to find the initial population. So now, the most common problem involves basically finding the value of K for our situation. Because if the pizza is in a certain room or on a certain type of pan, it's going to cool at a certain rate. If the carbon remains of whatever it is, an organism, a body, an animal, if it's frozen in ice, the carbon, like the radioactive carbon dating, is going to be at a different rate than if it was in the desert decomposing underground. So you have to calibrate K for your organism and your situation. So the process of carbon dating involves finding the value of K. So if you find a fossilized leaf and it contains 30% of its normal carbon-14, how old is the leaf? So we want to figure out how old this leaf is that we just found. The half-life of carbon-14 is 5,600 years. So what is a half-life? A half-life is however much you start with. Let's say you start with 20 grams of a material. It takes you 5,600 years and you still have 10 grams of the material left. So if it's uranium, whatever, radioactive uranium, the reason it's so bad is because its half-life is so long. So you still have the radioactive, whatever the nuclear waste is, radium or uranium. So it would take another 5,600 years and you still have 5 grams of whatever the material is left. It hasn't gone away. So then, it'd be another 5,600 years and you still have 2.5 grams of it left. So it takes a very long time to get rid of radioactive material. We're talking about carbon dating and the carbon breaking down. So we know that it's older than 5,600 years, right? Because it only has 30% left. If it was exactly 5,600 years, it would have all 50% of its carbon left. So we're going to show you how to calibrate K for this fossilized leaf carbon-14, then use the formula to solve for how old it is. So to find the value of K, you can use any starting amount of weight. So if I started with 20 grams of material, I now have 10 because I'm talking about half-life. E to the K times 5,600. I don't know K. I need to calibrate K. No matter what you choose for your starting weight, you put half the starting weight over here. See how there's no weight in my problem? I'm just making up these numbers. The very first step when you're solving for K is to divide by the starting weight on both sides, which will always give you 0.5 because half-life is the relationship of half as much. So I just kind of make up a starting weight so that I can show you where it is in the problem. If you want to skip to this step when you're talking about half-life, half equals E to the K times 5,600 is where you're always going to get to. So now I need to use logs to solve for K. Yes? Okay. All right, so I'm going to turn this into taking the log of both sides, or log form. I'm going to selectively use natural log because I see this base of E right here. So I'm going to take the natural log of a half equals k times 5600 natural log of e, because I'm bringing this power down in front, right? So this is what we just did on that other page. Natural log of e is equal to 1. That's why I chose natural log, because it's log e of e. So all I need to do on my calculator is take the natural log of a half and divide by 5600, and k should come out as a small negative value because it's decomposing. So natural log of a half divided by 5600 is negative 0.000124. Negative 0.000124. Is that right? Because it's to the negative fourth power. 1, 2, 3, 4. Yeah. So that's k. So I did all that work to calibrate k for this carbon-14 element. Now I'm going to take this k value and actually use it to solve for how old my leaf is. So see how they've already skipped ahead and put 0.3 right here? Just like I knew that when I took 10 and divided by 20, I'd get a half. They are down to 30%. So their equation is 0.3 equals E to the negative 0.000124 T. If you want to use the full decimal on your calculator, you can. I'm going to solve this problem the same way I just solved this problem. So I'd like you to solve for T. You could do it the same way I did over here. Take the natural log of both sides, divide by the constant, and it should give you time. Estimated it was more than 5,600 years old. Actually, if it had been 25%, right, it would have gone from 50 down to 25. It would have been exactly 2 half-lives old. So this is almost 2 half-lives old. All right, so the last thing I want to show you before we take a break for today is Newton's law of cooling. So E to the KT is in Newton's law of cooling, and it could be used for any liquid or the pizza, something that cools at an exponential cooling rate, basically. The formula looks complicated, so I would give you all of this information on a test or quiz or something. So you just have to be able to use the formula. So I'm just going to show you how to use the formula. So U of T is the current temperature at a certain time. So 20 minutes from now, how cool is your cup of coffee going to be? U sub 0 is your starting temperature. It's in Celsius, but on another problem, if you use all Fahrenheit, that's fine. Capital T is the temperature of the room. So like room temperature is usually around like 18, 19, or 20 degrees Celsius. For us, our starting temperature in Fahrenheit is probably around 65 or 70 degrees Fahrenheit for our room temp. And little t represents time, so how many minutes have passed. So here's our problem that we're going to figure out. Danny boiled water for tea. What does water boil at in Celsius? Do you know? 100 degrees, so that's important. So the water was boiling, right? That's the starting temperature, boiling water. After waiting for 3 minutes, he took the temperature of the tea, and it's now cooled to 60 degrees Celsius. So he's going to calibrate his cooling K constant. And then if he likes his tea at 40 degrees, or if this is a restaurant and they want to serve tea or coffee at 40 degrees, how much longer should they wait before drinking the tea or serving the tea? And it says assume room temperature is 21 degrees Celsius. So our first step is to solve for K, and our second step is how much time to get to 40 degrees. So we know that the current temperature of the tea is 60. So U of T is 60. I'm trying to solve for K. Capital T, the temperature of the surrounding medium is 21 degrees, plus our starting temperature we said was 100, so U sub 0 is 100. Subtract again the surrounding medium's temperature, so 100 minus 21 in the parentheses. E to the K times, it took 3 minutes. for that to happen. Are you with me where those values got plugged into the equation? So order of operations, 100 minus 21, right, is 79. And to solve for k by itself, I need to get this exponential part by itself first, the 79 e to the k times 3. So I would subtract this 21 to the other side to start with. So I have 39 equals 79 e to the k times 3. Now I need to get my e to the k times 3 by itself. So I'm going to divide by 79 on both sides. And I don't know what that is. I could just leave it as a fraction, or yeah, it's kind of a horrible decimal point, 4936. So let's just leave it 39/79 equals e to the k times 3. So I'm going to take the natural log of both sides because I need to take the log of both sides. I've got a base of e already. So I'm taking the natural log of both sides of my equation. So the natural log of 39/79 equals k times 3 times the natural log of e, which is 1. So I'm going to evaluate the natural log of 39/79 on my calculator in parentheses, and then at the end, divide by 3 to get my final answer. Natural log of 39/79, enter, divided by 3. Negative 0.235. Negative 0.235 is k. I'm running out of room. So my last step before being done for today, this is hard math. This is like the hardest thing that you need to do with logs and exponents. So k being this, now I'm going to reset the value up. It says how long should he wait now before drinking his tea? He wants his tea to be 40 degrees, right? The current tea is 60 degrees. So we're going to reset up the problem. We want the t to be 40, but the t is currently 6. Nope, that doesn't go there. We want the t to be 40. The surrounding medium is 21. The starting temperature of the tea is 60, right? Minus 21. E. So this is what I want. Surrounding medium, what I'm starting with, E. And then my k value is negative 0.235, and then I'm solving for t. See if you can solve that equation for t. How many? So you have to be careful to subtract this 21 to the other side, but divide by this 39. Sometimes people want to add this 21 and this 60, and you can't do that because this is in a parenthesis by itself. I tried dividing by the rounded answer and the full answer, and I still got 3.06 minutes. So if you didn't get 3.06, you did something wrong. But that kind of makes sense, right? Because think about it kind of as a half-life. For the t went from what, 100 down to 60, right? Which is almost 2/3. And then 60 down to 40 kind of is another 2/3. So it kind of makes sense that it took 3 minutes and then another 3 minutes. Alrighty.